free electron theory. Okay, so today we are going to start with the assumptions of that simplified model, which is talking about the conductivity of matters. Okay, so the assumptions are okay. So this is from where your syllabus actually starts. Rest, whatever we have discussed in the past lecture, that was just a background in order to connect you with the syllabus. Okay, so yeah. Transport properties of matters. This is your module 1. Okay, so let us talk about the features of electrical conductivity of matters. Some features of electrical conductivity of matters. So as I told you, any theory of the electrical conductivity of matters must explain a number of pertinent experimental facts, right? So the experimental data for the electrical conductivity which we are finding for matters, it must be in concurrent to the model which we are going to talk about, right? Theoretical model must verify the experimental data. So this is one of the major thing which we need to take care of. Apart from the deviations in the special cases or under extreme conditions, the general features of electrical conductivity of matters are, you can say, number 1, the current density in the steady state is proportional to the field strength. Current density in the steady state is proportional to the field strength, means applied electric field, you can say. Applied electric field. Then another important feature is the specific resistivity of metals at room temperature is of the order of 10 raised to power minus 5 ohm centimeter. Okay, where rho is the specific resistivity, rho is the specific resistivity of metals. You might be knowing what is the definition of specific resistivity. Specific resistivity is defined as the resistance of a wire of unit length and unit area of cross section, right? So I can say that this is the resistance when we have a wire of unit length and unit cross section area. See, when this L and A both are unity, then R is equal to rho. Okay, so this is the specific resistance. So most of the metals, they possess this specific resistance at room temperature. So this is another important feature. Then third one is, above Debye temperature, the resistivity of metals increases linearly with temperature. Means above debate temperature above debate temperature, resistivity is linearly proportional to temperature. Rho is proportional to temperature. Okay, and you might be knowing what is debate temperature because you have gone through the free electron theory as well as the lattice vibration chapter. Okay, so debate temperature, if you recall, debate temperature theta d, denoted by theta d, is the temperature of a crystal's highest normal mode of vibration. That is the highest temperature that can be achieved due to a single normal mode vibration. Okay, this is the highest temperature that can be achieved at a single normal mode vibration. Now you must be knowing what is single normal mode vibration and what is multi mode vibration, right? Single mode vibration means the you can see a normal mode of an oscillating system. This is a pattern of motion in which all the parts of the system move sinusoidally with the same frequency and with a fixed phase relation. Means if we have, let's say, n number of vibrations or n number of simple harmonic oscillators, you know that each electron is vibrating with its own natural frequency in any system, right? So if there are n number of free electrons in the system, means there are n number of simple harmonic oscillators in the system, right? So this is the single mode, means the if all these electrons, they are vibrating in phase with each other, right, with a single frequency, then we can say that the system is vibrating in with single mode. Okay, so this is single mode. This is single normal mode. Okay, so theta t is the debate temperature and is given by h nu m divided by k, where you know that h is the Planck's constant, nu m is the debate frequency, nu m is the debate frequency, and k is the Boltzmann constant. K is the Boltzmann constant. Okay, so this is the third one. Then next assumption is at low temperatures but above approximately 20 degree Kelvin, means at temperature above 20 degree Kelvin, the resistivity of many metals is proportional to T raised to power 5. Okay, so as the temperature increases, the resistivity drastically increases, and at a temperature above 20 degree Kelvin, the resistivity is proportional to T raised to power 5 for the metals. If I talk about the resistivity of some of the metals at helium temperature, at liquid helium temperature, you know what is liquid helium temperature? Liquid helium temperature means the temperature at which the helium could be kept in the liquid state, and this temperature is 4.2 Kelvin. Okay, so at liquid helium temperature, some of the metals exhibit a minimum in the resistivity versus temperature curve. Means some of the metals, they have minimum resistivity. Okay, minimum for some of the metals. This is only for some of the metals, this is not a common characteristics for all metals. Okay, so this is fourth point. And then fifth one is, for most of the metals, resistivity decreases with increase in pressure. Yes,
मैम एक बार प्रीवियस स्लाइड दिखाना.
just
Okay.
Yeah.
Thank you, ma'am.
Is that okay? Should I go ahead?
Yes, ma'am.
Okay. Okay. So fifth point is, for most of the metals, resistivity decreases with increasing pressure. What does that means? Rho decreases with increasing pressure. Okay, so reverse is the case with temperature. You know that resistivity of metals, it increases with increase in temperature. However, reverse is the case with the pressure. Rho decreases with increasing pressure. The next point is, according to, so this is another modification in the last free electron theory, the old free electron theory. According to Mathiessen's rule, according to Mathiessen's rule, the resistivity rho the resistivity rho of a metal containing small amount of impurities may be given by rho is equal to rho naught plus rho T, where this rho naught is a constant, which increases with increasing impurity content, right? So it means higher the impurity concentration, higher will be the value of this rho naught, okay? And this rho T is the temperature dependent part of the resistivity. This is the temperature dependent resistivity, right? So this is the sixth part. And then seventh feature is the resistivity of alloys which exhibit order-disorder transitions allows pronounced minima corresponding to the ordered phases. Okay, so there are some kind of materials which exhibit order and disorder transitions. For example, if I talk about let's say selenium, okay, it has a phase change phenomena, right? When you heat or when you apply temperature to selenium, at certain temperature it will have a endothermic process, right? So here the material is disordered, but when you apply the temperature more, it shows another phase which is exothermic phase, right? So in exothermic phase, the material is more ordered and more the molecules and the atoms are more systematically arranged. So this is a ordered phase. This is a ordered phase, and this is a disordered phase. This is a disordered phase. Okay, so there are certain materials which show ordered and disordered phases, right? So if you talk about the resistivity, whether the resistivity is higher in the ordered phase or disordered phase, I will say that the resistivity value is less at the ordered phase. So resistivity is less or having low value in the ordered phase. I hope you understand what is the meaning of ordered phase and disordered phase, right? Ordered phase means all the atoms, they are systematically arranged in the bulk of the material, right? Disordered phase means all the atoms are randomly distributed. Okay, so this is the 7th point. The 8th point is above Debye temperature means above theta D, when temperature is greater than theta D, the ratio of thermal to electrical conductivity is proportional to T. Just give me 1 second, please. Okay, so 8th feature is when the temperature is above theta D, above Debye temperature, the ratio of thermal to electrical conductivity is proportional to T. Means the ratio of K is to sigma, where K is the thermal conductivity and sigma is the electrical conductivity. So the ratio of both of these is proportional to temperature. This is small quantity and it is proportional to temperature. So this is here the metals follow Wiedemann-French law. So this is how this theory is different from the classical free electron theory. There we talked about that for all temperatures K upon sigma is proportional to T, but here we are talking about that at T greater than theta D, K upon sigma is proportional to T. Okay, the last feature is a number of metals exhibit the phenomena of superconductivity. Some metals, not all metals, but some metals exhibit superconductivity. What does that mean? The resistivity disappears at the temperature above absolute zero, right? Means rho becomes zero at a temperature above absolute zero. Absolute zero means 0 Kelvin or minus 273 degrees centigrade. Okay, so this is a complete combo, you can say, of the properties of the metals which has been experimentally verified, and here whatever things we are reporting theoretically, all those things they are experimentally verified. Okay, so these are the features of metals. Next one is the model. We are going to discuss a model which leads to the steady state, and here we are going to derive the expression for the conductivity and drift velocity, and then we are also going to discuss the relaxation time. So move to the next article.
मैम एक्सक्यूज मी।
Yes.
मैम प्रीवियस दोनों स्लाइड दिखा दीजिए एक बार।
Okay, this one.
मैम the previous one, previous to this one.
Yeah, this one.
Yeah, done मैम, thank you.
Okay, great.
Excuse me, मैम।
Yes.
मैम एक बार 4th point explain कर दीजिए।
Yeah. So 4th point is at temperature greater than 20 degree centigrade. This is for most of the metals, right? when you increase the temperature and when you reach at 20 degree Kelvin, so at this particular temperature the resistivity drastically increases for the metals, and now it is no longer proportional to temperature, but it becomes proportional to T raised to power 5. Okay, so this is a common feature for most of the metals. And at liquid helium temperature means the temperature at which helium can be maintained in the liquid state. Liquid helium temperature क्या होता है 4.2 Kelvin, right? So at this temperature, rho the resistivity is minimum for some of the metals. These are two different situations, right? This is a special case, this is a specific case where the resistivity is minimum for some of the metals at liquid helium temperature, right? But for most of the metals this pattern is followed. When temperature is increased and when the temperature becomes more than 20 degree Kelvin, the resistivity of the metals is no longer proportional to T, but it becomes T raised to power 5. Is that clear?
Yes, ma'am.
Okay, great. So should we move ahead?
Yes, ma'am.
Okay. So next article is a simple model leading to steady state, drift velocity, and relaxation time. Relaxation time. So now, as I told you, though the conductivity is also been derived by using the Drude-Lorentz theory, right, free electron theory, but here we are considering all the facts which actually resolve the drawbacks of the free electron theory. Okay, so let's see what is this model, what is the simple model which is talking about all these things. Okay, so in order to appreciate the essential problem in the theory of conductivity, it is useful to consider a simple model which shows the features of more sophisticated theory. We know that from the macroscopic point of view, the electrical conductivity of a metals is defined by Ix. Here I am assuming that the flow of electrons or the flow is along x-axis only. So Ix is equal to sigma Ex, and let's say this is equation number 1. Okay, where Ix is the current density, where sometimes you also denote it by using J, right? So don't get confused. You may say that this is Jx, right? Where Jx is the current density, where Jx is the current density, sigma is the electrical conductivity, and Ex is the applied external field. Uh, for an isotropic solid in which the electric field Ex is applied along x direction, the electrons will start drifting along x-axis, along negative x-axis, with an average velocity of, let's say, see, when you apply the electric field, what happens? Let's say this is the x direction. Okay, so this is x-axis, let's say. So when you apply the electric field over here in the x direction, the free electrons which are roaming around in the system, they will start drifting. they will feel a force, they will feel an external force, right? So these electrons will start drifting, and these electrons, they will move in a direction which is opposite to the applied electric field, right? So they will drift along negative x direction. Okay, now let us assume that if n is the number of electrons per unit volume, number of electrons per unit volume in the metal, and E is the electronic charge. E is the electronic charge, and let's say that when this external field is applied, the electrons start drifting with an average velocity of Vx along negative x direction. Okay, so it means that under such situation, the current density can be given by minus NeVx, right? You know this expression, पढ़ा है आपने इलेक्ट्रॉन थ्योरी में. Okay, so Jx is equal to minus NeVx, and let's see, this is equation number 2. See, when there is no external field, the velocity distribution is isotropic and Vx will vanish, right? See, this is all under the influence of the electric field. When electric field is applied to the system, अगर electric field नहीं होगा, then under that situation the distribution of the electrons will be random, right? See, one electron is like this, another electron is like this, another electron is moving in this direction, another electron is moving in this direction. So the distribution of the velocity is isotropic, right? This is in all directions, this is same in all directions. So under that situation, there will be no current because there is no directional flow of electrons, right? So under that situation, the current density will be 0. Right? If there is no electric field, if this Ex is 0, then Jx will also be 0. Right? But this is the situation when the electric field is applied to the system. Okay. Now, any free electron under the influence of an external electric field Ex obtains an acceleration, right? Because they are drifting, they are getting velocity, so they are getting an acceleration, right? And the value of that acceleration will be Ax is equal to minus Ex upon m. Why? Because force is equal to ma, and here in the electrical force, the force due to the electron that will experience the force due to the applied external field, that is equal to minus Ex. Okay, so यहाँ से you can find out the value of A. So A is equal to minus Ex divided by m. Okay, so Ax is equal to minus Ex divided by m, and thus velocity will continue to increase with time. Okay, so
that X is in subscript,
yes,
na?
yes,
Ma'am, that X is in subscript with capital
yes,
E,
yes,
electric field.
yes. This is a subscript Ex. It means that the field is applied along x-axis. Okay, this is a subscript. Please note that Ex. We are denoting E by Ex. Okay. Yeah. So it is evident that the influence of electric field alone would not lead to a steady state as required by Ohm's law. If we apply the electric field, then the velocity of the electrons will go on increasing, right? But the steady state will not be obtained under that situation. So it is therefore necessary to assume the occurrence of some kind of frictional processes, right? So this process, together with the influence of electric field, will then lead to an average velocity Vx, which is further proportional to the applied external field. Now what is this frictional process? As I told you last time also, see any electron when they are accelerated because of the applied external field, what will happen? They will collide with the positive ions inside the system. Okay, see, let us talk about this electron. So when this electron is accelerated by the applied external field, it will gain an acceleration, its velocity will increase, it will gain an acceleration, and it will so for a certain time its velocity will increase, right? And when it moves close to this positive ion, it will collide with the positive ion. It is going to be inelastic collision, so it will collide with this positive ion, and after collision the velocity will vanish. The velocity will it will decrease, and by the time it will become it may become zero, right? So this is the inelastic collision of the electron with the positive ion, right? So after the collision, the velocity of the electron will decrease, but due to the impact of this external electric field, this electron will again gain a velocity, and this will again be accelerated, and this will again move with start moving with the increasing velocity, right? So after that, it may also collide with another positive ion. Again an inelastic collision will occur, and again the velocity will decrease, but after some fraction of seconds the velocity will again start increasing due to the applied external field, and then this process will continue. Okay, so suppose the probability of an electron to collide with the lattice during a small time interval dt. We are assuming a very small interval time dt, and let's say that the probability of an electron to collide with the lattice ions during this small interval dt is dt upon tau, where tau is the relaxation time. So tau is the relaxation time, and you know that how to define tau. This is the time between two successive collisions. This is the time between two successive collisions. So 1 upon tau, it determines the probability of a collision per second. Probability of a collision per second. Okay, so dt is equal to dt upon tau. For this small interval of time dt, the probability of collision will be dt upon tau. Therefore, the rate of change of average velocity in x direction due to the field alone is given by dvx upon dt due to the applied field, ex, right, is equal to what? Acceleration minus E upon m, because acceleration is rate of change of velocity with respect to time. So this is equal to acceleration. This was your acceleration, right? Let's say this is equation number 3. Also, the rate of change of velocity due to collisions with the lattice alone, right? This is only the one part, right? When you are applying the external electric field, the electrons are drifted, and because of which the movement of electron is there. But the movement of the electrons is also there because of the collisions, right? So rate of change of velocity with respect to time due to the collisions is equal to what? Velocity, average velocity of the electrons per unit relaxation time, right? Or you can say velocity multiplied by the probability of collisions, right? So let us say this is equation number 4, where tau is the relaxation time, you know that, right? Now the net rate of change of average velocity with respect to time is what? Is equal to what? This plus this. This is due to the applied field and this is due to the collisions. Okay, so we have to add both of these terms. So this is dvx divided by dt due to field plus dvx, x is in subscript, please note that, this, and this is collision due to the collision. And we also know that this in steady state, this variation in velocity with respect to time is equal to 0, right? That's what we are taught in the free electron theory, right? So the variation of velocity with respect to time in steady state is 0. Okay, let us say this is equation number 5. So comparing equation number 3 and equation number 4, if you compare equation number 3 with equation number 4, see both of the terms, they are giving you the rate of change of velocity with respect to time. One is due to the field and another is due to the collision. But overall, when we talk about a system, the rate of change of velocity with respect to time will remain same for both, right? So it means that this right hand side will also be equal. So it means minus e on m is equal to Vx by tau, which further means that Vx means average velocity of the electrons is equal to minus E tau Ex divided by m. Let us say this is equation number 6. Now from equations 1, 2 and 6, right? From equation 1 and 2, let us see this is the equation number 1 and this is the equation number 2. So if the left hand side are equal, means right hand side will also be equal. So it means that sigma Ex is equal to minus NeVx, or Vx ki value we will substitute it from the equation number 6. So net result will be sigma Ex is equal to minus Vx, right? And Vx, the value of Vx, we are taking it from equation number 6, which is minus E tau Ex divided by m. Okay, so this means that sigma is equal to n E square tau upon m, because this Ex will be cancelled out by Ex. Okay, so this is n E square tau upon m is the expression for the conductivity of free electrons, the conductivity of matter.